Thank you so much for the invitation again. I'm super excited to show a little bit of the work that I was doing until now, and also why we are working on what we're working. And my talk is called Rethinking Tools in Digital Fabrication, a dialogue between the human hand and the robotic grip. As Leah already said, I'm assistant professor in Princeton University in the US. Also have an architectural practice in Innsbruck in Austria called mediate, where we work on performative architecture installations. And my research includes domains such as human-machine collaboration, construction robotics, interactive fabrication, adaptive computation, and extended reality systems. And I'm doing this work since several years. I did my PhD at ETH Zurich, as Leah already said, where I started to investigate these things when they were very fresh. AR was just coming to the market with open source software. And I started to investigate what all these new technologies mean for architects and craftspeople in relation to machines. And currently I'm doing all this work at EACVA, which is focusing on extended augmentation in architecture. I like this duplication of augmentation, where we actually investigate what it means to extend machines that already assist us. Here you can also see a picture of my lab. So I have a robotic fabrication lab situated in Princeton that focuses on small and large scale augmentations of the human with machines. Specifically, we work at EACVA on how technology as a primary mediator help us to structure our relationship with the built and the natural environment. So it's not anymore purely about the product or the outcome, but actually the act of interacting with the machine that's investigated in the lab, and what it means to interact with the machine. What do we need for that? Why did I start to get interested in that? When I started to work with robotics in architecture, I realized robotics in architecture is great, as you can see here. So it's very commonplace in architecture already, especially in academia, to have robots that help us build more complex, customized, and precise structures. Compared to digital fabrication, compared to manual fabrication, digital fabrication is very good at repetitive tasks, as you can see here. It's very good at lifting heavy loads, and we can provide high precision that we cannot do otherwise with manual fabrication. What's the problem with that? The problem is we are very far in academia with it, but we are not very far in industry or on the construction side. And why is that? I love this video because it actually shows what robots are very good at, especially in construction. Robots are very good at repetitive tasks, where the environment, as you can see here, is very structured, very ordered. The materials are always at the same location. Everything is well defined, and the sequence of actions is repetitive. What's the problem with that is if you look at construction sites, it's the complete opposite. We work with materials that are very malleable. We work with environments that are complex, that are not sorted, not ordered, and we work with humans. Humans are great, but the problem is humans are not very predictable. We don't really stick to the rules. We leave materials where we're not supposed to leave materials. At the same time, we humans are very good at specific things. So we're very good in understanding complex situations. So if you look at the picture on the left, we're very fast in understanding what is going on. If you look at the machine vision systems, it's very hard for them to detect what is happening. We're also very good with materials as mortar, as you can see on the right. So malleable materials that requires our dexterity with our hands. That's why we're very good with this. And this is also the reason why humans are still involved in robotic fabrication. As you can see here, a colleague of mine is placing joints of a timber frame to assist the shortcomings that we currently have with robotic fabrication. The problem is that the role of the human in these systems is still very marginalized. So first, the actions are not included in the control logic. So all the robotic actions are computationally controlled, but the human actions are not. And also what we can do in these processes is very limited to I would almost say, not the most interesting actions, or very restrained actions. And there are several reasons why we don't have kind of a better role of the human in these fabrication scenarios. The first reason is that most of our processes in architecture are feed forward. That means we produce a design, we produce a file, we send it to the machine produces. The problem with that is, if what we are not happy with what the machine produces, we have to go all the way back to the beginning and start again with the design. The second thing that is directly linked to these computational problems that we have is an inflexible distribution of tasks. So that means we have projects or processes that are solely for the human to fabricate, and processes that are solely focusing on the machine to fabricate. What is the problem with that is, if we have an inflexibility, that means if there are processes that require both, we need to decide at the beginning for which actor do we design the computational model in the background. And the third very important thing is, if you want to include humans more intelligently in these processes, we need more human interaction interfaces. So more intuitive ways we can interface with the machine. And this is a little bit the vision that I have. Currently, what you see is that's processes that are kind of standard in architecture. Is we have a human that sits behind a protective shield and the robot is fabricating, which leads to delays in fabrication, leads to not very interesting fabrication scenarios. So it's either machine or human, or it leads to processes that does not take the full advantage of what we could have if we combine a human and the machine. And the vision that I have is more the one on the right, where it says we start to overlap all these agents in the same workspace. So that means humans and machine work more collaborative together, interacting and communicating with diverse technology. And I want to show 4 projects in an overview. They're all papers on these things. So if you need more technical information, I invite you to read papers. I rather want to talk what it meant to develop these projects. I want to start with a project that is coming more from an art environment. It's called Degrees of Life. It was part of Co-Reality, an art and science research project in Vienna that we did for 4 years. It was supported by the PEAK, by the Austrian government. And it investigated what it meant to make an architecture that is created and alive through the interaction between humans and machines. And specifically, I was interested in how the gaze is influencing how an architecture grows or dies in relation to the human. You will see that all of the project that I'm showing talks a lot about why is it important that we humans are present in the fabrication or production of architecture. This project was done together with Barbara Imhoff and Tiziano Derme and the University of Applied Arts in Vienna. Here you can see we had a huge consortium of other researchers coming from microbiology, coming from artificial intelligence research, other architects, microbiologists, because the project was a 4-year project where we actually investigated what it meant to truly not just envision these scenarios, but trying to produce as closely as possible to it. And the exhibition was at Zentrum Focus Forschung in Vienna. Here you can see a final picture of the vision of the exhibition, where we said we had environments where humans could interact with, and specific elements changed in these environments depending on the presence of the visitor of the exhibition. So that means the human presence was able to manipulate the fabrication with, specifically there we worked with bacteria to create biomaterials. So Degrees of Life was the first full-scale proto-architectural installation, testing the results of the research of this 4-year Co-Reality project. Degrees of Life aim to develop this interactive environment that I just explained within an architectural space. So the idea was that architecture can learn, grow, and decay in relation to human presence and human behavior. So for the non-verbal behavior, I'm very interested in how humans human and living materials. They were using an eye tracking device. It was able to detect where a visitor is looking at. and what exactly they are looking at. So the exhibition was articulated around three self-sustaining closed environments, as you can see here, hosting three different types of bacteria. And so although these environments were able to self-sustain themselves, we tried
Daniela, sorry to interrupt. Just your sound is not very stable. Can you repeat again and try me to talk directly to the microphone? The sound is just not stable.
Can you hear me?
Yeah, no, it's good.
So this exhibition tried to, can you hear me?
Yeah, we hear you well.
Perfect. So this exhibition tried to investigate what it meant to have this kind of interactive architecture as a living system. Here you can see these three different self-sustaining environments. One with Escherichia coli, one with the sucro fermenter, and one with cyanobacteria, and an eye tracking localization station where people could register themselves to have their gaze tracked. So all these environments relied on this human interaction and the mechanical actuation to thrive. And here you can see how I'm interacting with the Escherichia coli environment. This was the eye tracking device. So the human interaction was registered in real time by a wearable eye tracking device that recorded the human's local position and pupil gaze direction with three different cameras, with a world camera, with an eye camera, and a tracking camera. So the overlaying of these three cameras could tell us where exactly a human is looking at in space. Here you can see a picture of that. And this allowed us to actually record conscious actions such as the gaze direction and unconscious human actions such as gaze duration and pupil diameter. So this eye tracking was used to start an interaction routine and visualize the data in real time onto the space. So we had a projection in space that could tell other people what the person is looking at. And depending on what environment the person looked at, the exact gaze location within this environment and the intensity of the gaze, that means pupil diameter, time of gaze, frequency, a corresponding machine within this environment was activated. And then this machine either stimulated, fed, visualized, or directed bacteria growth and behavior within this environment at specific spots where the human looked at. So, and all three environments were triggered according to the needs of the hosted bacteria. So you can see the Escherichia coli environment, we had sodium hydroxide, sucro fermenter, we had nutrients, and for the cyano environment, we had light that activated the bacteria behavior and then either produced more material, so like with the sucro fermenter environment, or created a color change, as you can see in the Escherichia coli environment. So this was the Escherichia coli environment. This environment focused on a color change in real time initiated by human interaction and the metabolic process of the bacteria. And the human interaction released a specific amount of sodium hydroxide at the precise point in this closed environment where the human actually looked at. And this led to a change in the pH level in the culture, which then resulted in a specific color, as you can see here. And through the metabolic process of the bacteria, the color slowly changed back. So we had a real-time color change here, where you can, for instance, envision this could be applied to facade systems or other parts of a building. Here you can see a sucro fermenter environment. This was especially focusing on growth of biomaterial, and the human interaction activated the spray nozzle to drive a defined spray location and spray nutrients. And where the spray nozzle sprayed the nutrients, the material started to grow. In the cyanobacteria environment, we hosted a specific genus of cyanobacteria, and the bacteria obtains energy via photosynthesis. Therefore, we worked with light. And the human interaction changed the light conditions of the environment by switching the bacteria's growth strategy from photoautotrophy, so light periods, to heterotrophy, dark periods. And then it started to create what you can see here in green, different mats that you can see here. I like to start with this project because it starts with the most abstract and then jump directly to something that is, on the first glance, more applied to architectural research. Discussing a similar thing where we say, okay, does it make a difference if the human body is involved in the creation of architecture when a machine is producing. I always say this is kind of the idea of what is this digital human touch, why is it important that we're there. And for this one, I would like to introduce interactive robotic plastering, which is an augmented interactive design and fabrication for on-site robotic plastering, where we combine augmented interactive design with a robotic plastering process. Here I work together with Selen Erkan, who's working on plaster spraying. And the case study included the construction of an on-site design over a period of 3 weeks, where we design and fabricate on-site without a predefined model. And it was the first time that the plastering process was paired with an interactive fabrication setup. So here you can see all these 3 components that I just mentioned. There are an interactive design setup, an augmented reality system, and a robotic plastering setup. IROP, so interactive robotic plastering, uses a controller-based interaction system, as you can see here, to enable humans to build interactively design and fabricated articulated plasterwork in situ. So for this, we thought that it's interesting to take the building structure and the as-built state of the ongoing fabrication into consideration while you're still designing outside. And it also allows humans to create complex digital models in minutes and rapidly generate multiple design alternatives, with the idea that it allows humans with limited programming skills to instruct the robot by demonstrations and generate complex digital models. IROP consists of a stylistic filter selection. I explain in a second what that is. So it's a specific computational setup that lies behind the entire software. A user interaction tracking setup with projection mapping for the interactive design mode, and a robotic plaster spraying setup. The software of IROP has 3 different key modes. The first one helps humans to define an aesthetic style of the plasterwork. So this means that humans don't come to the site with a finished design, but actually they just pick a style similar to Photoshop brushes, where you just pick what do you want to have, a rough brush or a soft brush, and this is then translated into 3D space. So these styles allow humans to translate and remap their physical actions into analog output, into robotic output. So that means this style system allows creativity while ensuring that whatever the human is designing interactively still complies with material and machine's constraints. So to give an example, this is one of the styles I created, which is a carving effect versus a smooth spraying effect. So the closer the hand was to the spraying interface, the more it created this carving effect. And the carving effect is actually inherent to the fabrication process we used because of the plaster that is still liquid and the air of the spray nozzle. The liquid plaster gets distributed. So the closer the hand is, the more you get this rough surface, and the further away in your design process the hand is to the spray surface, the smoother the plaster wall. So by using these filters, humans can creatively and intuitively adjust the texture of a plaster. The second key mode of the software is an interactive design mode. You can see here this design mode had different levels. So it allowed humans to have audio-visual guidance to instruct humans while designing on site. So you can see here the different actions were linked with different audio. In the beginning, I always thought it will, it's kind of a nice gimmick, but it might not be very useful. And in the end, we realized it was super helpful to have additional audio inputs while we interact with the machine on site, because the construction site is so visual, distracting, that we need audio or multisensorial input while interacting with the machine.
Welcome to the construction site. Please mark the points on the ground.
So here you can hopefully hear the sound that we had in parallel.
Points are marked. Projection is starting. You can start drawing. Welcome to the
So you can hear and see that this was the interface that people used. And to test what it actually means, we went to an abandoned construction site where we moved our robot, we moved our audiovisual systems, and we designed and fabricated there for 3 weeks. The students also used my computation setup to define new filters or these aesthetic styles to test with this glass spring, going from left to right to very one-to-one translations of human movements, so a hand drawing filter, to a very abstract translation of human movements called an agent-based filter. Students used actually exactly the middle, so they used the tweening filter, which is middle between a lot of human input. So humans actually placed every fourth curve, and the transition between these curves was automatically generated. Here you can see how we actually fabricated on site. So for 3 weeks, we went in, we designed at the beginning of the day, and then we fabricated with the robot what we designed. And in these 3 weeks, we evaluated, did we find something that actually has an interesting aspect of this combination of on-site design and fabrication. And here you can see the result. Students actually decided that they didn't want to have one kind of master drawer, but every student used the system over time. And what I found especially interesting were these kind of micro gestures that are very hard to, or it takes a lot of time to generate this in a CAD system, a computational setup that we architects usually use. And it had a lot of more variety, small changes, kind of jitters in the drawn line that I thought especially interesting. In the first two projects, I show especially show mostly the machine fabricating and the human instructor. During my PhD, and I'm still working on this, these parts of the project, is this idea of what if not just the machine is fabricating, but machines and humans are fabricating in parallel. And I started with investigating that with a project called Tie a Knot. Tie a Knot is a combination of manual and machine assembly of complex wooden structures using rope charts. Here, I was especially interested, as in the other two projects before, of how we can include human actions into the computational model to create a digital twin of the entire construction scenario where you have the human actions and the machine actions registered in real time in the same computational environment. Here I was, similar to IROP, interested in what if we do not come with a final design to the construction site, but we make design decisions on the fly during fabrication. Here I worked together with Lydia Atanasova from the TU Munich in what now became almost a 3-year research on different timber assembly structures with mobile robots and humans. Here you can find the paper. So maybe we stop on this picture a bit because it actually shows quite well the different aspects of the project. So for Tie a Knot, I tried to evaluate how we can combine this manual and machine assembly of complex wooden structures using rope drawings, as you can see. To enable this interactive workflow with humans and machines in the same workspace. So before in IROP, you saw them next to each other. Here we are working in the overlapping work environment of humans and machines. I worked on turn-taking tasks. So that means a human is doing an action and then the robot is doing actions. For Tie a Knot, I worked specifically with 2 humans and 2 robots. You will see later I expand this to an indefinite amount of humans and an indefinite amount of robots. Before we saw that the human was doing a lot of the creative decisions rather than the physical actions. In Tie a Knot, I'm also evaluating what can we do physically different to a machine, especially robotic actions that are very known to that it can do way more physical actions. I split it in 2 parts. So human tasks were to place elements that are difficult to place. So robotic actions are hard for elements that are intricate to place or hard for elements that touch surfaces, because Surfaces are never where they actually should be in a digital model. So especially for these moments, a human is way better because we can adjust in real time very fast. I distribute the physical task of tying knots, so for the joints to the human. This is something that is incredibly hard for a robot to do. And to adjust the digital model in real time, so track manually placed elements. The robot was tasked to place elements that had to be precise. So especially in mid-air or in the middle of the room, which is something that's super hard for us humans to do. Also, I used the robot to stabilize elements. So that means to reuse the robot during fabrication to hold the structure up while the human is continuing to fabricate. Specifically, the structure worked on smaller units. So here you can see, I call them Y triplets. And these Y triplets are part of the bigger logic of the entire structure. So these Y triplets are made of 3 struts, one from a previous element, here you can see it in gray, one placed by a machine, here visualized in blue, and one assembled by a human to close the triplet, so here you can see in yellow. So multiple of these Y triplets define then the structural logic of the entire system, a reciprocal spaceware. And to stabilize the structure and to connect the struts, we chose a manual rope joint connection, as you can see here. I picked rope joints because I was interested in asking the question of how we can combine manual joints with super precise robotic fabrication. And also this part examined the architectural potentials of such a cooperative assembly. And now I want to guide you quickly through a process of how would you design and fabricate with such a system. So we have 5 important steps. This is the first step, the interactive design. So it means humans were able to decide in which direction the structure is growing in real time while fabricating. So for this, we picked which Y triplet is the starting point of the next Y triplet. After we chose the starting point for the next Y triplet, the second strut is then placed by the robot. The third step was to close the Y triplet with a manually placed element. And due to the nature of reciprocal frames, the third element was the hardest to fit in and therefore distributed to the human. The human did not need to know exactly where it had to go, so it could make a free decision on the exact rotation and placement of the third element. And the fourth step was to connect all 3 struts with rope joints. As the third strut was placed manually, it needed to be tracked to be included in the digital twin because the other 2 were, of course, already precisely placed. And for that, I tested 2 different tracking systems. One was visual inertial object tracking, where I collaborated with Timothy Sandy on. And the second manual option was with a robot where I probed 4 reference points on a strut to define position and rotation. And to test the feasibility of the entire concept, we built a proof of concept timber structure, changing the design of the structure on the fly. This project led to continuous investigation. What I really liked about this project were the distribution of tasks, so that the human was placing the joints and the robot was placing the precise elements in space, and the balance that we needed to do to have to create this this structure. What made it very difficult is something that I conceptually like a lot. So the open design was quite difficult to produce fast enough because we had a lot of discussions on site, and it led to a lot of different decisions where we did not have enough feedback. So we didn't have enough structural evaluation on the fly that could inform us on is the decision that we are doing a good decision or not a good decision. So these questions led to the next projects, which continued this idea of collaborative narratives. And it also led to the understanding that we need to have more interfaces, especially when we work with robots. You saw in interactive robotic plastering, we had the spraying, but I was never informed on where the robot is moving. So that's why we could actually not, that's why we were situated next to each other and not overlaying in the same work environment. In collaborative narratives, it is two projects actually. One was for which is called collaborative augmented assembly at TU Munich that we built up at the Future of Constructions symposium in 2023, and the right one is something we did last year in Toronto for a symposium on robotics, investigating different aspects. So the one in Toronto that you can see on the back is actually the one we advanced the software the most with augmented reality timber assembly. Both of them, so here you can see collaborative augmented assembly, which resulted in the tree structure, did not have anymore the changing of the design on the fly. The intricate rope joints moved to more industrial connector joints to also investigate what it would mean for an industrial setting to produce something like this in a fast time. Here we had 5 days for students to work on the system, where we started to develop a lot on the visual interface design. And for ARTAS, or augmented reality timber assembly, we developed a lot on the robotic interfaces that we need to produce. This one was at RobArc 2024, where we also won the best workshop participation, investigating this assembly of humans and robots. Specifically, what I found very interesting in the development of these two projects was, what does it really mean if we then overlap this environment, where we use a phone for interacting with the robot and instructing a human during fabrication? So this idea that we have to localize humans and robots to the same coordinate system. So this idea of what does it mean precision-wise to put both agents in the same digital model. Here you can see one of the processes for both of them, where we used mobile robots, as we also used in tie and knot, but we extended it that we actually can control the robotic actions with the phone interface. We can preview what the robot is planning to do, so the human can actually navigate their actions depending on that. Also, we extended it that it can be an indefinite amount of robots and humans, so we can start to work together in assembling these structures. So here you can see a picture of the augmented reality app that I was developing for ARTA, where you can see in yellow the little figure that is where I am supposed to place an object, the current object that is actually active, and the robot that is placing in blue the next object. This, of course, is a simulation, and once I approve it, the robot will do this action. And the human also gets instructions for the manually assembled elements, as you can see here, so they get a lot more input on how do they need to place the joints, which element do they need to place. And what is completely new here compared to anything I showed you before, the tasks between what a human should place and the robot should place, these tasks were interchangeable. So a human could change on the fly what they want to do. And this was something that we discovered was extremely important. It was actually used a lot in the production, because even though we have a lot of computational models that help us make decisions while we sit in front of a computer, a lot of decisions happen while we fabricate. So that means we need to be able, in this task distribution, to have this flexibility that allows a human to pick an element to place, or sometimes say the next 3 elements can be placed by a robot, even though they're distributed to me as a human. And here you can see a video of how such a process would look like. Humans would use a phone to register. They would localize. They can see, let's say, the next element should be built by a robot. They can request a toolpath planning for the next element to place it. They can preview the actions that the robot needs to do to place this element, so they can predict the movements of the robot with the AR app. And they can execute everything of the robotic actions while not leaving the fabrication environment. What is also interesting, they can preview, if they use mobile robots, where the mobile robot has to move. So this is something that we found very interesting, because if we talk about robotic mobile robots, of course, we envision that they know where to drive themselves. But if you want to talk about speed, it's good to already place them in close proximity of where they have to go exactly. And also you can see here the humans place the joints. In this scenario, it was a metal swivel joint that you could screw to increase stability and also speed of fabrication. And then you can see the next element again was placed by a robot. You can also see here that we actually use the robot for stabilizing the structure while continuing to fabricate. So I love this picture because it shows, especially with the project we did in Toronto, how many hands work at the same time, and it looks chaotic, but at the same time the placed object is then fed back into the computational model, and all of these hands are informed by the same computational system in the background. Also here, where you see the robot placing or stabilizing one element with notes for the human on the structure, QR codes on the structure. I'm already coming to an end where I just want to show what all this research led to. It's something that's very close to my heart, which is Compass XR. I really realized that, especially in architecture, engineering, construction, this development of interfaces is something that lacks a lot. And one of the reasons I think it is that we do not have open source software that specifically targets problems that we have in architecture, engineering, and construction. So XR interfaces that we have either have to, everyone at different universities always starts from scratch, or we use libraries that we have to adapt a lot. So I started to develop Compass XR in collaboration with ETH Zurich, which streamlines the standard reality workflows to ease the implementation of human-machine collaborative applications for architecture, research, and educational environments. And the whole idea is that we make XR interfaces that allow us to talk via cloud services to different users. So phone-based users, so humans, so this can be also headsets, computers, so that means architects that sit in the office, and robots at the same time. So this idea of multi-user, multi-agent digital fabrication process. And how it works is we have different user-facing devices. That means applications or apps on the phone that tells humans what to do. They are linked directly with the HUD environment, so a digital environment where architects are designing, and they're talking via different communication protocols to each other. That means the system of how many user devices are linked to Compass XR is completely open. That means we can have a construction process involving 10 or 100 people talking to 10 or 100 robots at the same time, while all of them are informed in real time about the actions of each agent in the entire system. And for that, we developed a specific computational protocol. Here, the design of the ARTA structure by Lydia, where we use the system that explains not just the geometric attributes of a structure, but also the underlying computational idea, where we say, where we use a graph-based network that talks not just about the geometric attributes, but also the relationship of this object to the entire structure. So this allows us to create something like this, where we have an assembly. So I always like to take the example of a brick wall, where you say each brick is part of this assembly as a node and has a relationship to the other bricks, which is then described via the edges. And this allows us to create, to inform not just about the individual, so a brick is a geometric form of a brick, but also who places this brick, when should this brick be placed, and have something like on the right where you say each brick on the first layer needs to be built before you can move to the next. This is very important if you have multiple people work on one structure, because of course you don't want them to start to build something that cannot be built before you finish working by it. And then we used the software to test on different case studies. So CAA in 2023, you saw already where we developed the interface on it. Augmented timber assembly we used to investigate especially multi-users and robotic control. We used it at Princeton for allowing students to develop their own apps. So we investigated, is it easy for people to use that to create something entirely different? And grammatical research at ETH Zurich used it to create a really large-scale timber structure, timber tower, to also investigate how flexible is the system for different application scenarios. And one thing that is close to my heart is that it is open source. So if you're interested in using it, please go ahead and use it. This idea of sharing the research that we're doing is something that I find truly important. So everything is open source in GitHub and published to the Python's packaging in Index. So we also have a very detailed documentation available online. We moved the GitHub, so please refer to this GitHub instead of this one. This is the old one, where also we show example files and we show step-by-step instructions on how to use composites. With that, I want to end my presentation. Please reach out if you're interested in the research that we're doing, or if you're interested in collaborating. You saw that I do a lot of collaborations because I find it truly interesting, not just humans and machines to collaborate, but also different universities to collaborate. So shoot me a message if anything of that triggered your interest. So thanks a lot.
Thank you, Daniela, for the very interesting talk, and I will give now the stage to the audience for some questions. Manuela, yeah.
Hi there, thank you very much for your really informative talk, especially for somebody who's not in the field. I have one question, because this interaction in human and robotic technologies as a collaborative sphere, in how far does motion capture, if you look at, for example, virtual studio ecosystems with the Unreal Engine and the now more and more financially available motion capture full body suits like Rococo Suite or something like that. In how far do these pose possibilities to, in real time, create physical embodiments of the human actor in the world of the robot, so that there is a sort of more intuitive coexistence, more intuitive, less dangerous shared working sphere? What do you think? Is that something where developments are heading, or is that something that is solely in the sort of 2D visual representation, get things into a virtual camera, or is that also something that could go into production, architecture, and other fields?
Thanks a lot for your question. Actually, you're on the right track. We have, on top of, here in Princeton, we have the robotics, the robots on the ground floor, and we have a motion tracking system on the top. And we have one research now that investigates more embodied interaction with the robots. There are two, so I always like to track human actions in two ways. So you can track human actions by the placement of an object, right? So if I place a cube from here to here, you could predict that there was a human action placing it from here to here. So this is one way to kind of try to understand if something happened in space. Or the other one is you track directly the human body in space by seeing if there was an interaction. There's a little bit the danger some of my colleagues doing that as research, where they just directly translate one-to-one the human action to a robotic movement. I find this not that interesting. The reason for that is I think human bodies work very differently to robotic units. So that means we can do a lot of more behavior than the mechanics of a robot can do. And I think so there needs to happen kind of a translation between what a human is doing, what is the intention, so the higher intention of the human, and then translate kind of the intention to the robotic unit rather than the one-to-one translation. I always say that the reason for that is we never do the same task repetitively. So there are studies where they observed someone hammering a nail, and it was not really that much of the hammering of the nail. So how do you hold the hammer? This is always somehow slightly different, but it's the act. So we observe, does the nail do actually what we predict the nail to do? So it's the act itself, the intention that we want the nail to go in, that is interesting, rather than exactly on how do we hold the nail. So when it comes to translation from I want the robot to do some specific action, I tend to not directly translate and track what is the human doing. So there are these tendencies in which we just train it, but I try to train it on the intention and leaving it to machine learning systems to figure out what does the robot need to do to reach that goal. So we have, for instance, now a research project that works on predicting of actions of humans with machine learning, where the robot tries to understand what is the goal that the human is doing and what do I need to do as a robot to reach the same goal. I leave it to the robot to find a solution for that, because often we cannot even think of the right solution, and using machine learning helps us a lot with that. So on mocap or the motion capturing that we talked about, I mostly use to detect things in space. And by this detection of things in space, having a kind of a logic underlying that tells me what does that mean that, let's say, two timber pieces are now close to each other. So this is currently how I'm using it.
Okay, thank you for the explanation, Daniela. Are there any further questions? Yes, Frederic.
Thank you. All great work going on. I was wondering what kind of responses you get from the actual construction world on one side. Do they see this as long-term results eventually, or are they thinking that this can happen soon, that some of the work you do would be useful to them? So that's the construction world, and you mentioned the difficulty of real construction sites, and I'm wondering how close are we from applications? And then there's the world of architecture itself in terms of new possibilities. Is there interest from professional architectural firms in this space? These are my two questions.
Thanks for your question. It's interesting because construction is one of the slowest moving industries when it comes to tech. The reason for that is it works quite well and everyone earns enough money, so there is no urgent need to do that. The urgent need comes from something else. The urgent need comes from we do not have enough construction workers anymore. So less and less people want to work on a construction site. So even though currently there's no, so for instance, bricklayers, there are not many bricklayers anymore who want to become bricklayers. So all the research that I'm doing has 2 points. First, if we can outsource to a robot part of the tasks, that's great. But I also want that it stays socially sustainable. That means we do not want to completely get rid of all of the jobs. So that means the best would be if the creative intellectual decisions stay on the worker on site or the craftsperson. So this allows actually an upskilling of the work. That means you're not anymore purely doing the physical labor, but actually you're also in charge of doing cognitive decisions on on site. So this is one of the reasons where I see like it will become more important. Whenever I give the software and systems that I'm producing to construction workers, I'm always super surprised how excited they are. I always thought if you show them the software like this, they will be, no, that's very academic, we don't want to handle with that. And actually it's very different. They treat it as any other tool they get. They try to learn it, try to understand it, and try to use it. So from the construction workers, it's people like it a lot. With architects, I have a lot of discussions because architects, a lot of the software that I'm doing says that not the entire design work is done by the architect, but actually also the people that are producing the work. Architects tend to be a bit more sensitive when it comes to this sentence. I truly believe that the construction worker or the craftsperson has a huge influence on the final result. Why not give them also the kind of tools to do this more integrated and not just kind of secretly, okay, it happened and we don't talk about it. So this is still a little bit of a discussion that I have every single time with architects that say, we like our methods. Do you want to get rid of the architects? I always say no, but I think we need to become more open when it comes to the collaboration with the different other humans that are involved in the production of a building or a structure. So this is a little bit to the how people perceive the research. Generally, more and more people, especially in digital fabrication, go or want to use this software. It's also why we started to develop Compass XR. I realized often it's very simple problems that we need to do, and academia is always very far ahead with all our problems. So I'm solving problems for mobile robots with multiple humans and multiple robots, while on the construction side, we don't even have an AR headset. So Compass XR tries to kind of provide both simple industry solutions at the same time involving academia, so providing more complex problems like mobile robots. Because you have to kind of provide both, otherwise you lose either academia or you lose industry. So Compass XR is the first approach to exactly your question of like, what do we need to do to translate some of this research back to real world applications.
Thank you very much, Daniela, for this closing note and for joining us all the way from Princeton. We would like to continue to our next speaker. So thank you very much, Daniela. It was really a pleasure having you.
Thank you. Thanks for having me.